Hi class, this is the class video for Tuesday, December 8th. We looked more at BCA tables again today. We did not get to the acid-base reactions. In terms of expanding stoic to these things, we got to mass examples. We'll look at these examples in class on Thursday. And we did not get to completely set up the copper mining lab, but get your materials ready for Thursday. Or I gave people the option of setting this up on their own. There is a video on Google Classroom in the assignment that you can watch. So I will give you 10 minutes on Thursday to set these up. It's a quick setup of this test tube. And then we made this quiz a practice quiz due to several absences. So that's on Google Classroom. And if you were not here on Tuesday, you should take the quiz. It's supposed to take you 20 minutes, and then take a picture of your work and attach that to the assignment. And I should mention that homework, there is a stoic worksheet on Google Classroom. This will be due on Friday. There's also an AP Classroom watch the 4.6 videos and take notes and attach those to Google Classroom. And you can also work on the Unit 4 AP Classroom questions. These are due on Monday the 14th. We also said that we would be moving the Unit 4 quest. That would be moved to Monday, December 14th, to give some people who have been absent a little extra time to prepare. Okay, so we spent some time doing some review questions of the previous day to see how people are doing. So first of all, this question shows a particle model based on this balanced equation, and the question asks what should be shown in the products here. So here, if we take a look, we know that 1p4, here's 1p4, reacts with 6H2, and that will give us 4 pH3s. Okay, so in our particle diagram, we need to have 4 pH3s, so 4 here. And then what's not reacting here are these 5p4 molecules. So the answer to this question would be 4pH3 molecules and 5p4 molecules in the product side. What would be the limiting reactant? So if we go back here, we can see that these P4 molecules are excess. Okay, so these are the excess P4 molecules. Therefore, the limiting reagent is H2. H2 gets all used up. Okay, and there's none left after that reaction takes place. We reviewed the solubility rules, so there are 3 solubility rules that you need to memorize. So the rules are that group 1 salts, any ionic compound with a group 1 ion is soluble. Nitrates, NO3-, these are soluble. NH4+, those are soluble. So all of these are soluble, okay, or they will be labeled as AQ, aqueous, dissolved in water. And so these are the solubility rules that you need to memorize. And so here, if we take a look at these 6 ionic salts, the ones that are soluble are going to be definitely this NO3, right? This copper 2 nitrate will be soluble because of the nitrate. Definitely B, because it is an ammonium salt. And then not these things, okay, because not silver chloride, not calcium sulfate, okay, because they're not in this group of solubility rules. That does not mean that they're definitely not soluble. We just don't need to know about them, and we'll be given information about whether they are or are not soluble. And then E is also soluble. So these 3, we can recognize that these are going to be labeled as AQ in a balanced reaction. And the others we don't have information about. If we are asked information about these, we will be given the information so that we can answer the question. All right, then review of net ionics. So we first need to complete and balance this equation. So this is a double replacement. We have 2 ionic substances. Their ions will switch places. So we're going to have PbCl2. The Pb is a +2 ion. Let me put these ion charges in here to help me. And so we have to write the correct formulas based on the charges. And we have NaNO3. Now we want to put in the states of matter. Nitrates are going to be aqueous, soluble. Sodium salts, that's the sodium is group 1, again, aqueous. Here, we don't know, this doesn't apply to any of our solubility rules, but it says that a precipitate forms in this reaction. And if we look at the last substance, sodium and nitrate are both soluble. This is aqueous, so this must be the precipitate. So we'll label that as solid. So then we need to go and balance this equation. Looks like we need a 2 here, and we need a 2 here. Okay, now, so we did that. We're going to write the complete ionic. So for the complete ionic, we're going to break up, dissociate any soluble ionic substances like this lead nitrate, the sodium chloride, and the sodium nitrate. So we'll break apart each aqueous compound into its ions. Oops, let me go back here. When we get to the PbCl2, that's a solid. It's the precipitate. We do not break that apart. That stays together. Then finally, the 2Na plus and 2NO3 minus. So we can see here we've broken up things into their aqueous ion. Just recall that we made that chart of what dissociates and what does not dissociate. And we need to keep that in mind here. So if we take a look, in order to write the net ionic, we have to cross out the spectators. NO3 appears on both sides, 2NO3, and also 2Na also cancels out with this, so the net is what is left over. And as you expect, it is what the ions that are forming the precipitate. So there's our net ionic equation. Here's another equation, but this time the states of matter are given to us and the balanced equation is given to us. So again, here we take a look at each substance and decide whether it should be dissociated or not. And just as a reminder, a review, right, there's a list of things that we wrote that we need to separate into ions and other substances that we keep together. Okay, so remember, dissociate means to separate into ions. So here are group 1, our nitrates, our ammonium. Those things get separated into ions. Those substances, so any soluble ionics. And then we also have our strong acids and bases that get dissociated. Here we keep together our solids, our precipitates, our liquids, our pure gases, and we also keep together our weak bases and acids. Okay, so that's a brief overview of the things that we dissociate and things that we keep together. So here, this solid, we are not going to break apart. It's just a element. The AgNO3, this is a soluble ionic compound, nitrate. So we break this up into its ions. Okay, and then our Ag solid, we do not do anything with that. Keep that together. And this is going to be Na plus aqueous plus NO3 minus aqueous. The only things that that we can cross out is this nitrate. So that's our complete ionic right there. And then our net would be Na solid plus Ag plus aqueous forms Ag solid plus Na plus aqueous. And that's our net ionic equation. So then we spent some time answering some questions on the chemical reactions lab. A couple different things on that lab that we went over, and then there was time to work on the practice quiz on Google Classroom. So after the break, we started talking about particle models again and BCA tables. I wanted to spend a little more time going over the BCA table and particle models to make sure that people understood how our particles connected with the box with the BCA table and how to use the balanced equation. So the balanced chemical equation, the coefficients there, which I'm squaring, these coefficients are the ratio of how these substances react. Okay, it does not tell us what we actually have. That's given in the problem. Those amounts are given in the problem. This only tells us how these substances react and gives us the ratios between the products and the reactants and the reactants and the reactants. So when we're drawing a particle model, we could always draw the products here. However, in problems, we will not always get particles. Okay, we'll get moles or grams or pressure, and we need to relate this through moles. Okay, these coefficients are the mole ratios or how the moles react. In the BCA table, right here, The only time we use these coefficients is in the change row, okay? And also, let me add this in, and in finding the limiting reagent, okay? And I'll abbreviate the limiting reagent as the LR. And the ratios, again, come from the coefficients in the balanced reaction. So here we have a particle model of the reactants. We're going to fill in our before line with the reactant amounts. The before line represents what is present in the reactants before the reaction starts. Now, of course, we could draw some particle diagram and get the results, but the idea is that we want to be able to do this without drawing the picture, because we're not always going to have a picture. We're not always going to have particles. So here in our before line, we can see from the particle diagram that we have 4 nitrogens and we have 9 H2 molecules and we have 0 ammonias. So that's what we fill in right here. Now, before we do anything, before we do the change line, we first always, we have to find the limiting reagent. Okay, we have to figure out which reactant is the limiting reagent. The change right here, this comes through the limiting reagent, okay? So we can't figure out or use the ratios unless we know what the limiting reagent is. So here, if I look here, 4 N2s, what I want to do is I'm going to take my 4 N2s and I want to figure out, if I have 4 N2s, how many H2s do I need to react all of the 4 N2s away? And what I need to use are these coefficients. Okay, so I can see that the ratio of hydrogen to nitrogen is 3 to 1. So if I multiply this, right, I get 3 H2s for every 1 N2 particle. The N2s cancel out, and I get 12 H2s. That means that I need 12 H2s to react all of the 4 N2s. And if I look here, I do not have 12 H2s. I only have 9. Therefore, I don't have enough of the H2. My H2 is the LR, the limiting reagent. My N2 is in excess. Okay, so now that I know what my limiting reagent is, I can go ahead and start filling in my change line. For the limiting reagent, that always disappears completely in the reaction. So I'm going to just subtract off the 9 and get 0 here. Now, looking at the N2, I want to figure out how much N2 reacts with my limiting reagent. Okay, the change line is based upon the limiting reagent. So here, what I want to do is I want to take my 9 H2s, okay, my 9 H2s here, and figure out how many N2s I am going to react with it. And I can see that for every 1 N2, I use 3 H2s, so I can put that ratio in here, 1 N2 over 3 H2. H2s cancel out. And I get 3 N2s. So here, I will subtract off 3 N2s that are being used, and 4 minus 3 is 1. So I'll have 1 N2 molecule left over. Here I can see that I have 2 NH3s for every 3 H2s. If I start out with my 9 H2s, again, the limiting reagent, and I want to figure out how many NH3s I'm going to get, my ratio is 2 NH3s for every 3 H2s. And that will give me 6 NH3s. So here, it's a product, so I'm going to produce it. This is going to be positive. And now we have our result. And so in our products, This after line, okay, represents the products. Okay, we can draw in 1 and 2 and 6 NH3s. So here's my 1 and 2, and I'll have 6 NH3 molecules. Okay, and I'll draw in my hydrogens here. Okay, so there's my particle model, but you can see that we could find that particle model through the BCA table. Here is another example. Okay, so again, this example is with a balanced chemical reaction here, the combustion of methane. Here, we do not have particles, we have moles. Okay, so we can fill in the moles here, the amount that we're given, and they're asking us for the moles of carbon dioxide that are produced. So here, 1.5 moles of methane, we'll put that in here. 1.7 moles of oxygen. And these are 0 initially. Okay, we have no products to start with. Next, we want to figure out which of these is the limiting reagent. So again, here, I'm going to take my CH4. I have 1.5 moles of CH4. I'm going to figure out how much O2 I would need to react all of that away. So if I multiply by my ratio of 2 to 1, so 2 moles O2 over 1 mole CH4, I can see that I need 3.0 moles of O2. And if I look here, I've got only 1.7. So oxygen is the limiting reagent. Okay, oxygen is the limiting reagent. The methane is in excess. So let's subtract away the limiting reagent. Now let's look at the coefficients of these things here. So here, the ratio is 1 to 2 for methane to oxygen. We want to change this 1.7 into the methane that reacts. So we can take that amount, the 1.7 moles of O2 right here from the change line, and figure out how much CH4. Well, I have 1 to 2 ratio, so 1 mole CH4 for every 2 moles of oxygen. That will give us 0.85 moles. Let's put in our units here. And then this will be negative because we are losing reactant, and that will give us 0.65 moles. Over here, our coefficient for CO2 is 1. Well, that is the same coefficient as the methane, so we know that the change has to be the same, and it has to be positive because we're producing it. Here, this coefficient, the H2O, is a 2. It's the same as the coefficient for oxygen. So whatever change happened to the oxygen, it's the same change for the water, except that it's positive. Then we can just add these. And get these amounts here. And so we can easily answer now how many moles of carbon dioxide are produced. That would be this number right here. 0.85 moles of CO2 are produced. Then I asked the class to do this problem. And so it'd be good idea if you haven't seen this yet, to pause the video and to try this yourself first. So in part A, we first are asked to balance the chemical reaction above. So here we can balance the reaction by putting a 5 in front, and there's a 1 and a 1. In part B, it gives us that 0.75 moles of P4O10 and 0.5 moles of oxygen remain after the reaction. After the reaction in a closed container. What were the initial amounts of phosphorus and oxygen? And it says to use a BCA table. So we're going to set up a BCA table. Okay, try to make it nice and neat here so that you guys can actually understand it. All right, so again, it says 0.75 moles of P4O10, 0.5 moles of oxygen remain after the reaction. Key word here, after. So we're doing the after line here. We've got the products this time, not the reactants. Okay, so we want to put in here the 0.75 moles. And we want to put in 0.5 moles here for the oxygen. And 0 here, right? There's none of this left. It doesn't say anything about P4. And then we want to work backwards to get these initial amounts of phosphorus and oxygen. So we know that initially there should be 0 product in the beginning. Okay, if we start out with these two things. So we know that this change line here has to be 0.75 moles. All right, so now that we have this one change quantity, we can fill in the rest using stoichiometry. So if we take a look here, how much oxygen was needed to produce this 0.75 moles of P4O10? We can write that out, 0.75 moles P4O10. And the ratio is 5 to 1, so 5 moles O2 over 1 mole P4O10. So that times 5 gives us 3.75 moles of O2. So I can put that in here. This must be subtracted because it was a reactant and it disappeared. So then if I work backwards, this should be 4.25 moles. Okay, and we can do the same thing with the P4. The coefficients for P4 are 1 to 1. So this change here, this is produced by the same amount of P4. So that's minus 0.75. And so to get 0 at the end, this must have been 0.75 moles to begin with. So the answer to part B, we can answer that right here with these numbers. Okay, so we can say that the initial amounts were 0.75 moles of P4 and 4.25 moles of O2. All right, and then the last part of this asks us for the grams of phosphorus. So if we start off with 0.75 moles of P4, we need to multiply that times the molar mass of P4, which is 123.88 grams per mole. And we can get the grams that way, right? Multiply by the molar mass, and we get 93 grams of P4. So that gives us the answer to part C. So once we can actually use BCA tables and use the mole ratios to find reactants and products, we need to add in the other ways to get to moles, because we can't measure moles in the lab, right? Moles, there's no moles balance or mole scale. There are several different ways that we can get to moles. So the most common thing that you probably immediately thought of is by using the molar mass to get to mass or grams, right? We can easily convert between these two things by using our grams per mole or our molar mass. The other thing we can do, we've been looking at particles, is we can convert moles to particles by using 6.02 times 10 to the 23. So sometimes they might ask you to calculate the number of particles. They could ask you for particle diagrams where you don't really have to calculate, but just look at the particles. The other way that we've talked about, another way, is concentration. We can convert from moles to using concentration. And remember, concentration means molarity. That's the kind we are using, our moles per liter. Okay, remember that if we take our molarity times our liters, we get moles. Okay, so that's another way. The other thing we can do is we can convert to volume, or go from volume to moles, or pressure. Go from pressure to moles. And we can use the ideal gas law for this. So we can go to volume if we know the pressure and temperature, or we can go to pressure if we know the volume and the temperature. The other thing, recall that at STP, at standard temperature and pressure, we have 22.4 liters per mole. Okay, so that's going to involving gases here. Another connection is density. So we can go from moles to mass and volume as well. So we could go to mass or volume through density, because density equals mass over volume, and moles are related to mass. So these are the ways that we've talked about. Later on, we will also talk about how we can convert the amount of energy released to moles. And we will also talk about how we can convert the charge or the voltage to an amount of moles. So right now, these are the main ways, and I'll star the most important ways that we've learned. So mass to moles, very important. We're going to do this all year, right? Mass to moles all the time. Concentration, for a good portion of the year, we'll be using concentration. Hugely important. And then whenever we talk about gases, we need to be able to convert between volume and pressure and moles. So some vocabulary that you may or may not remember are these terms called the theoretical yield. So this is always a calculated amount that is found using stoichiometry, okay, and the balanced chemical reaction. We always have to calculate this. We always need to calculate the theoretical yield. The actual yield, on the other hand, is what you produce in the lab in an actual reaction. This is always measured. This is a measured quantity, the actual yield. So the percent yield is the actual yield over the theoretical yield times 100%. And this is not on the equation sheet. Memorize this if you need to. I like to look at this popcorn analogy. So popping popcorn, if you start out with 30 kernels, your theoretical yield would be 30 kernels, 30 popped kernels. However, if you look at this picture here, imagine this is your lab. You look at this and you say, oh, 1, 2, 3, 4, 5, 6, 7 have not popped. So my actual yield is only 22 popped kernels. And then we can find the percent yield by taking 22 over 30, and that will give us our percent yield. So percent yield would be 22 over 30 times 100. So before we go on to look at a couple examples, remember some of the skills that you need is to understand chemical formulas, write balance equations, know how to use these coefficients as ratios, calculate molar mass, converting to moles in all sorts of ways. You might want to add some things to this list. For you, maybe it's different. Maybe there are other skills that you want to add. So here's our first problem type. So these problem types that we're going over, this is not the whole exhaustive list of types of problems that you could encounter. But this is a large example of them, and stoichiometry is so important. You'll use it for the rest of the year in chemistry. It is kind of like the bread and butter of chemistry. So important to understand this. So in example 1 here, this is a mass stoichiometry problem when the limiting reagent is identified. Okay, they tell you what the limiting reagent is. So here we have the iron reacting with oxygen to form rust. Iron 3 oxide is shown below. Here's the balanced chemical equation. How many grams of rust are produced from 125 grams of iron reacting with excess oxygen? So if you want to try this yourself, I would pause the video here and give it a try, and then proceed from there. Okay, so how do we do this? Well, first of all, right here, we see that 125 grams of iron react with excess oxygen. So I'm going to label my equation here. This 125 grams goes with my iron. Put that there. And then it says with excess oxygen. So I'm going to identify this as my excess. That must mean that this iron is my limiting reagent. And also that's the only number they give us. So I'm going to show you 2 methods to solve this problem. And there are more methods than 2. There are several different methods. There's probably like 5 common methods to solve these problems. But these are the 2 methods that are most commonly used. And I guess these are the 2 methods that I would think about using. So the first step, well, the first method is to use a BCA table. To use the BCA table, we have to first convert our 125 grams of Fe to moles. Okay, so I'm going to change that to moles. .24 moles of Fe. Okay, so that's how many moles of Fe I have. I can put this into a BCA table. And I know that initially we have 2.24 moles of iron. This is excess. And the question is asking about rust. We don't care about what happens to the O2, so I'm just going to ignore my O2 for now. I know I have 0 of this to begin with. Just as before, we need to get rid of the limiting reagent completely. That's 0. Then let's use stoichiometry to figure out how much rust we should produce from 2.24 moles of Fe. So I take my 2.24 moles of Fe. I multiply by my 2:4 ratio here, 2 moles Fe2O3 over my 4 moles of Fe. Okay, and that will give me 1.12 moles. And I can put that as plus 1.12 moles. And that's what I produce. So that's how many moles. They're asking for the grams. So I now just need to take my 1.12 moles of Fe2O3 and multiply by the molar mass of iron 3 oxide, which is 159.7. And when I multiply this out, I get 179 grams of Fe2O3. Okay, so that's our first method. That's using our BCA tables just as before. The second method that I'm going to show you, method 2, I would call this the dimensional analysis problem. Well, problem solving method. So what I can do is I can start off with the amount they give me, which is the 125 grams of Fe. I convert this to my moles. Okay, we're always going to go to moles first because, right, the only way to get from one thing to another is through the balanced reaction, and that reaction gives us mole ratios. Then I'm going to use my balanced reaction, the coefficients. And you can see that a lot of the same things that we did with the BCA table are showing up here again. And then finally, that gets rid of my moles of Fe. I now just convert this to grams, 159.7 grams per mole. And I get 179 grams of Fe2O3. Same answer as with the BCA table. Okay, so now in example 2, we've got a mass-mass problem. Okay, going from mass to mass, but this time we need to find the limiting reactant. So in this problem, silicon carbide, SiC, is commonly known as carborundum. This hard substance, which is used commercially as an abrasive, is made by heating SiO2 and carbon to high temperatures. And here's the balanced reaction. So in part A, it says how many grams of SiC can form when 2.50 grams of SiO2 and 2.50 grams of C are allowed to react. So there, I can look at this and say, oh, I've got 2 reactant amounts. I've got to figure out the limiting reagent. And then we'll read part B. It says how many grams of the excess reagent is left over after the reaction. So first, before we attempt any method at all, right, when we're faced with a limiting reagent, we need to figure out which reactant is limiting. Okay, so to do this, I have to go through moles again. So I'm going to take my 2.50 grams of SiO2. I'm going to change it into moles by dividing by the molar mass, which is 60.09. This gives me 0.0416 moles of SiO2. I next have to take my carbon grams and change that into moles so that I can compare the two. So when I divide this out, I get 0.208 moles of carbon. Okay, so what I want to do is figure out which of these is the limiting reactant. So if I take my moles of SiO2 and I figure out how much carbon I can react with that. So if I take that and I use my ratio here, I can see that for every, I get 3 moles of carbon for every 1 mole of SiO2. So I can multiply these out. I get 0.1248 moles of carbon. And if I take a look here, I've got 0.208 moles of carbon. This is larger than what I need to react all of the SiO2. Okay, so this is my excess. And my SiO2 is the limiting reactant. Okay, so before we even go on to choose a stoich method, okay, we always have to figure out the limiting reactant before we can now figure out what our grams of SiC are produced. So here again, method 1, I'm going to show you the BCA table. So set up your equation. All right, so now here, let me put my mole amounts in. So I've got 0.0416 here. I've got 0.208 moles of carbon. I've got 0 of these. And frankly, if looking at the questions, I could probably just ignore this column, but I'll fill it in anyway. All right, my limiting reactant, again, we said that that was the SiO2. So let's subtract that off. 0. We already, from our limiting reactant calculation, we know that the amount of moles of carbon that react with the SiO2 is 0.1248. So when we subtract that off, we get 0.0832 moles. Over here, my SiC ratio, my coefficient is 1. That's the same as the SiO2. So I know that that will be the same change, except that it's positive because it is a product. And here we have twice as much as the SiC or the SiO2. So I can take 2 times the 0.0416 and I get 0.0832 moles. Always good to keep your units. So here 0.0416 moles, 0.0832 moles. Okay, so now going back to the question, we want to know how many grams of SiC can form. So here for part B, take this times the molar mass. Okay, so if we take 0.0416 moles of SiC times its molar mass is 40.1 grams per mole. Can multiply that out. And I'm getting 1.67 grams of SiC. Okay, so then part C asks how much of the excess reagent is left over. Remember, the carbon was the excess. So here's my leftovers right there. I can just take my 0.0832 moles of carbon times 12.01 grams per mole and multiply that out. And I get 0.999. It's 2 sig figs, maybe 3. That would come out to 1.00 grams of carbon. Let me fix that 1. Okay, that's 1.00 grams of carbon left over. Okay, so that's the BCA table method to answer this problem. What if we had to use our our method 2, which is our dimensional analysis method? I can, again, if I want to use my dimensional analysis, I still first have to do this and figure out what the limiting reagent is. Once I do that, I can take my 0.0416 moles of SiO2. I can use my mole ratio of 1 mole SiC for every 1 mole SiO2, and then multiply by 40.1 grams per mole. And I will get 1.67 grams of SiC. All right, so that part seems faster than filling in a table, but what about the excess reagent? So that was part B. Sorry, am I calling these A and B? Sorry, I should relabel this. This is B. This is A. Okay, back here. This is A. And this is B. Okay, so for part B, we want the excess reagent. We know that's the carbon. We have to figure out how much carbon is used up in this reaction. So you can see that here it's all set up for you in the BCA table, but in using the second method, all we have is this. We know the moles of carbon, and that's about it. So what we can do is take that moles of SiO2, that's our limiting reactant, figure out how much carbon is used to react that limiting reactant away. So in our balanced equation, that's 3 moles carbon for every 1 mole SiO2, and then multiply that by 12.01 grams. Okay, and when we do that, we see that this comes out to 1.50 grams of carbon. And this is what is used. Initially, we have 2.50 grams of carbon. So if we subtract off the 1.50 grams, what is left over is 1.00 grams of carbon left over. Okay, so, this method works perfectly fine too. You just have to keep a little bit of better track, right? It's not organized for you like in this BCA table. You got to spend a little more time thinking about what quantities you need to find and what those quantities represent. Okay, so I hope this helps. Next video is going to go over more examples, and please email me if you have any questions.